All right, we're here in section 2.6, and we just got our useful theorem and extension for finding limits at positive or negative infinity. And so recall, we said that the limit as x approaches positive infinity or negative infinity of 1 over x to the r, where r is any rational number, that limit is going to be 0 because the denominator of that function gets so huge that the result becomes tinier and tinier when we say that the limit is 0. Okay, so now how are we going to use this? Well, these are going to be our new limit tricks here. So trick number 1 for finding limits at positive or negative infinity. This is going to be to multiply everything by the reciprocal of the highest power. It's kind of a long sentence here, but we'll get the trick. Multiply everything by the reciprocal of the highest power of x in the denominator. Okay, so let's see what we mean by this. All right, we've got ourselves a little limit set up right here. Example 1. The limit as x approaches infinity of 2x minus 3 over x minus 4. Okay, we are going to use this trick, multiply everything by the reciprocal of the highest power of x in the denominator. Okay, so for starters, the highest power of x in the denominator is going to be x to the first power. Okay, so there is our highest power. It was either the first power or the 0th power, so we'll take the first. So highest power of x is just x to the first. And so the reciprocal of that, remember reciprocal means flip, flip that fraction over. So reciprocal is 1 over x. Okay, so we are going to multiply everything in this entire function by 1 over x. So let's do that. 1 over x multiplying our numerator, 1 over x multiplying our denominator. Okay, and then we still haven't calculated a value yet, so we got to keep writing limits. But we're going to have, here I'll write it, 2x minus 3 times 1 over x, then x minus 4 times 1 over x. You'd want to distribute that 1 over x to both terms in the numerator and in the denominator. So you're going to have a limit as x approaches infinity of 2, because the x's cancel out, minus 3 over x in the numerator, and then in the denominator we'll have 1 minus 4 over x. Okay, now we can see here, well, hopefully we can spot our little useful theorem and its extension involved in this. So notice here, let me use a different color of highlighter. But notice these expressions right here, 3 over x and 4 over x. That's a constant divided by x to some power, like this. A constant divided by x to some power. And we're taking a limit as x goes to infinity. So those two expressions highlighted in purple, the 3 over x and the 4 over x, the limit of both of those pieces is going to be 0 as x gets very, very large. And that's how we're going to be using our theorem and extension. We let those pieces become zeros. Okay, so here I'll keep that highlighted and make a little note here that we get to use our theorem / extension on these parts. Okay, so use the theorem extension on these. As x approaches infinity, 3 over x is going to approach 0. And same thing for 4 over x, and 4 over x approaches 0. Okay, so that is where we're going to get to plug in an actual number. We get to plug in 0 in place of 3 over x and 4 over x. So we get to stop writing limit, and we say 2 minus 0 over 1 minus 0, and we get our result of 2. Okay, so that is the limit as x approaches infinity of this function right here, 2x minus 3 over x minus 4. As x gets very, very large, the function values taper off and approach a value of 2. So thinking of our original definitions here, that would mean that this third definition kicks into effect. This function is going to have a horizontal asymptote at y equals 2. So that's worth noting. Let's write that little note. Note. This means that 2x minus 3 over x minus 4 has a horizontal asymptote at y equals 2, because that's what the function values, the y values are approaching there as x gets very, very large. Okay, so yeah, that is how trick number 1 is going to work for us, multiplying by the reciprocal of the highest power of x in the denominator. Okay, let's do one more here. All right, check out example 2. We're going to take the limit as x approaches infinity of 2x cubed minus 3x squared over x to the 4th minus 4x. All right, so we identify our highest power of x in the denominator. That part should be pretty straightforward. It's right here, it's x to the 4th. There's our highest power. It's x to the 4th, and so the reciprocal is going to be 1 over x to the 4th. So that's what we're going to multiply everything in the function by. So multiply by 1 over x to the 4th, 1 over x to the 4th, numerator and denominator. Okay, now I'm just going to do the distribution right from here. So distribute that to both terms. We haven't used any values, haven't plugged anything in yet, so keep writing limit. And in the numerator, some of those x's would cancel. We'd have 2x cubed over x to the 4th, so that would be 2 over x ultimately with that distribution. And then our second term here would give us negative or minus 3 over x squared. Okay, so there's our numerator. And now in the denominator, let's distribute. We'll get a 1 and then minus 4 over x cubed. Okay, So once you've done that, once you've distributed and simplified things down, you see what could be used with our theorem and extension. Okay, so any constant over a power of x. So constant over x to some rational number. That would be 2 over x, 3 over x squared. All right, that's a constant over x to some power. And then 4 over x cubed. All right, all three of those can get the theorem and extension applied. Okay, so all of these are going to approach 0. Okay, according to our theorem. So that means we can plug in zeros for each one of those purple highlighted terms. Any constant over x, we get to do a 0. So 0 minus 0 over 1 minus 0. Okay, and so we're going to end up with a limit value of 0. Okay, so that means that this function is going to have a horizontal asymptote at y equals 0. Now, the problem didn't specifically ask us about horizontal asymptote, but it's going to tie in, so it's worth mentioning. It just asked us to find the limit, though, and we would say that that limit is 0. So, one last thing here. For rational functions of these types, so rational functions of the form r of x equals a sub n x to the n power plus a sub n minus 1 x to the n minus 1 dot dot dot. So you're going to just keep taking those powers of x down until you get to a constant plus a sub 0. This is just a fast way of writing a polynomial in generic terms. Okay, so polynomial, generic. All right, so this is a generic polynomial here. One on the top of the rational function, one down in the denominator. Notice how each one of those has a different degree to it, highest power of x. The numerator polynomial is of degree n, and the denominator polynomial is of degree m. I'll try to make those sound as different as possible on the recording here. So numerator is n, denominator is degree m. Now we have a couple shortcuts we can use for these rational functions, and this all comes from applying that trick number 1, multiplying by the reciprocal of the highest power of x in the denominator, and then applying our theorem and theorem extension. So these you can always do by using that trick. It's just if you want a shortcut, here it is. So if m is greater than n, so the denominator has a higher degree than the numerator, then the result that we get for limit as x approaches infinity of this rational function r of x, it's always going to be 0. So we just saw that in example 2, actually. The denominator was degree 4, the numerator was degree 3, and the result did turn out to be 0 for that limit. So that's going to hold true for any rational function of that form. All right. Now, if m is less than n, so the denominator is of a lower degree than the numerator, then the limit as x approaches infinity of r of x is actually going to approach either positive or negative infinity. This one is not quite so nice of a case where we get a good constant, something like that. Okay, it's just that the numerator is still going to have a power of x left in it that we can't apply our theorem and extension to. So there's still going to be an x in the numerator growing and growing without bound. And so our limit is going to approach positive or negative infinity. All right, so this case here doesn't have a horizontal asymptote. Okay, because it's not a constant there. Now, the last case, if the degrees are equal, so if m equals n, your polynomials in this rational function are of the same degree, then get a nice result for this limit as x approaches infinity of r of x. It's going to equal the fraction or ratio a sub n over b sub m. Okay, and you might recognize those here in our rational function setup. A sub n over b sub m. Those are the leading coefficients of the polynomials. So that's what we have here, a sub n, b sub m. These are leading coefficients. And you take the ratio of those. That quickly can calculate the limit for you. And we saw one of those in example 1. Okay, here with 2x minus 3 over x minus 4, our polynomials are of the same degree. They're both degree 1, x to the first. So our leading coefficients are a 2 and then a 1 right here. So this quick shortcut here says our limit as x approaches infinity should be the ratio of those leading coefficients. That would be 2 over 1, which is 2, exactly like we had found. All right. So yeah, again, you can do this with the process with multiplying by the reciprocal of the highest power, use the theorem and extension. Get used to doing that because you can't always use these shortcuts. But if you want to use them, there they are.